Okay, so let's start out. Let's talk about electric forces and fields. So we have Coulomb's law, which gives us the force between 2 point charges, or it gives us the magnitude of the force. And of course, like charges repel each other, opposite charges attract. And I'm going to do two problems with forces, a one-dimensional problem and a two-dimensional problem. Or maybe related to this, so another way of looking at the force, how do these particles interact with each other? We have this electric field, which is a property of a single charge. So let's focus on that, because once we find the electric field, very easy to find the force. So let's say we have a positive charge here. Let's say we have two positive charges. And they're separated by, say, 8 centimeters. So we can place the origin here. So here are the two charges. Say Q1 is 4 microcoulombs. And Q2 is 6 microcoulombs. And let's say we want to know the electric field at x equals 6 centimeters. So we use linear superposition for this. We can find the electric field due to each charge individually at that point, and then we add them up, adding them as vectors. So to start with, let's look at, imagine you're at this point here. And since electric fields move away from positive charges, E1, the electric field due to Q1 at this point, would be to the right. So you can think of it, if you're at the point where you want to know the electric field, move away from positive charges and move towards negative charges. Now, E2, again, we move away from charge 2 because it's positive. So E2 would point to the left. So what we have to do is find the magnitudes of E1 and E2, and then add them as vectors. And because it's a one-dimensional problem, adding will be much easier. We don't have to break anything into components. So we'll just see which one is bigger. That's the way the electric field is going to go. To get the magnitude, we would subtract these two values for E1 and E2. So, this one won't be too bad. I might kind of cut down on the number of actual, just set up the problems and maybe skip the actual calculation part to save time. But for now, let's put the K. So it's about 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q1 is 4 microcoulombs. Q2 is 6 microcoulombs. And again, it's very important when you're doing these that, in this case, both charges are positive. But if one of these charges was sorry, I'm just looking for E1, not the force. Okay, so if E1 was negative, you would not put the minus sign in there. I really should do it like this, just because just to remind just as a reminder that we're talking about the magnitude of the electric field. The direction depends on where we are. So like right now, if we had, say that was a negative charge, we get a negative sign, you might think, well, that's to the left. But if you're on the other side of the charge, it should point in the opposite direction. So all we care about is the magnitude of the charge. You never want to put the minus sign in the way we're doing this. And then the distance from x equals 0 to x equals 6 be 6 centimeters, and we square that. So we'll get newtons over coulomb out of this. Yeah, the meters squared cancel out. One of the coulombs cancels out. So units are going to be newtons over meters. 9 times 4 is 36, and 6 squared is 36. So that's going to work out nicely. So we just have 10 to the 13 over 10 to the 6. So we have 1 times 10 to the 7th newtons per coulomb for E1. Now E2, kind of the same thing. So Q2 is 6 microcoulombs. And then the distance is 2 centimeters. We're going from, charge to the point in question from 8 to 6. And we have to square that. So this one, 9 times 6 is 54 divided by 4. Let's see. Yeah, let's use 6 over 4 is 1.5. That'd be like 13.5. And times 10 to the 7th. So a much stronger electric field, E2, and that should be expected because not only is the charge bigger, but we're also closer. The distance even matters more in this case. So we've got these 2 electric fields, and obviously E2 is going to win. So the magnitude of the electric field because they're pointing in opposite direction, we would subtract the magnitude. So 13.5 times 10 to the 7 minus 1 times 10 to the 7, 12.5 times 10 to the 7. And that's the magnitude, and it would point to the left because E2 was bigger. Okay, so that's a one-dimensional problem. And you want to be careful of the Q, couple things. First off, when you plug in the Q, forget the plus or minus sign. We're just looking at magnitudes. Make sure you get the direction of the electric field right. So again, imagine yourself at the point and you move away from positive charges towards negative charges. And then add them as vectors, which in the one-dimensional case is easy, but we'll do a two-dimensional problem as well. I think on that one, I might cut down on the calculation part and just outline the procedure, just so we can cover more material today. But any questions on this one? Okay. So let's do a two-dimensional problem now. And again, that's all we'll do is 2 dimensions. We're never going to go into 3 in this class. That would complicate things significantly. So a 2-dimensional problem, that means that we have, like say 2 charges, could have more, but say we have 2 charges, which we can just place them both on the x-axis. But we also have a point where we want to evaluate the electric field. And yeah, let's put that on the y-axis to make things easier. And so, yeah, 3 points, that typically defines a plane. But if we have like a 3rd charge, then we can go to like a 3-dimensional problem where we want a point. So if we have like say 3 charges, this board is the only plane that contains all those charges. So if we wanted a point somewhere that's not on the board, that'd be a 3-dimensional problem. Same basic idea, but the math would become more complicated. It's harder to look at angles in 3 dimensions. All right, so yeah, we have a lot to cover. So let's more or less outline the procedure and not spend too much time doing actual calculations for this one. So let's say Q1, let's say that one is negative, and Q2 is positive. And typically, we measure things in microcoulombs. So we want to find the electric field at this point, which is 3 centimeters above Q1. So just like before, imagine you want to find the electric field at this point. So imagine you're here, and remember you move away from positive charges and towards negative charges. So we're going to have E1 and it's going to be in that direction because Q1 is negative. So you move towards negative charges. And then Q2 is a positive charge. So we would move away from Q2. So drawing the vectors, we've got those here. One of them is conveniently just along the y-axis, so we can we have to break this one into components, but E2 we'd have to break into components. So we're going to have to add these two as vectors. So it's good to make a table. Say we have E1, E2, and then E, which is the resultant electric field. And then we have our X and Y directions. So before we actually calculate magnitudes or anything, what I'm going to do is let's look at E1. Now E1 points straight down. So the X component of E1 is 0, and the Y component is negative because it's pointing down. So again, what we're going to do is we're going to find the magnitudes E1 and E2 just using that formula. And then we get the directions just from looking at the picture. So the magnitude won't give us a plus or minus sign. So E2, in the X direction, we're going to go to the left, so that's negative. So we go left and up. So now what we would have to do is find the magnitudes E1 and E2. And let's not do the calculations. I will do this though. So for E1, that's 3 centimeters. So KE, that's our known constant. Q1, that's given. but we have to get the distance r. So let's write that down. Now E2 be KEQ2. Again, just the magnitudes. Now this is R2, which we have to find. So again, we have a right triangle here. That distance is 3. That's 3. So r squared would be 3 centimeters squared plus 3 centimeters squared. So that would be 18 centimeters squared for E2. So this one, we can get rid of the parentheses here and say 9 centimeters squared. Okay, so again, it's very straightforward to find E1 and E2. And here for E1, once we get this value, we just put it there. There's no breaking anything into components. E1 is purely in the y direction. Now for E2, we have to break things into components. So let's do this. Let's define this angle as theta. That would make this angle theta as well. And because it's 3 by 3, we don't have to do anything with a calculator or anything like that. Those are both 45-degree angles. So let's draw this. We have E2, which is a known magnitude. That angle is 45 degrees. So the x component, we would use cosine. So x is adjacent to the angle, so we use cosine. The y component is opposite, so we would use sine. Now, in this case, sine and cosine are the same because it's a 45-degree angle. But you want to get these right because usually that won't be the case. And of course, then we would plug this in here and this one in there. So we're skipping the actual calculation part, but just going through the procedure. And then once we have this table complete, let's just make this kind of ridiculous drawing here. So like whatever we get here would go in that cell. And now we're practically done. If we want the electric field in component form, because we would just add these columns. Or so 0 plus whatever that is. That would give us the electric field will have a negative x component. As for the y components, I'm thinking it's going to be negative as well. Yeah, because Q1 is a bigger charge and we're closer. And it's, E1 is directly down, where this one is only a component. So yeah, the net electric field would look something like this. And that would give us the electric field in component form. If we wanted to convert to polar form, let's just draw one more picture. So say our electric field points in this direction. Here's EX, here's EY. Let's define that angle as phi. Then we can say that E squared is EX squared plus EY squared. So we want the magnitude of the electric field. And then we can say tangent of phi would be EY over EX. Now, I highly recommend, if you're going to do this, that you look at EX and EY as just magnitudes. You, like in this case, they're both negative, and it would actually work out in this case. But I would just put in the actual numbers here without a plus or minus sign. And the reason is we're taking an inverse tangent, and you will get an answer, but not necessarily the one that you want. So if you just take the inverse tangent, you will get, in this case, it would work out fine. But yeah, we could realistically have problems where you could get the wrong angle. So if you just look at magnitudes, that would give us this particular angle. And then if you want to write it in standard form, you would add 180 to that, because this angle here is phi. So like in the standard form, you start from the positive x-axis and go counterclockwise. So that'd be 180. That would be that additional angle we'd have to rotate through. So if you didn't have a picture to display, if you were just typing this or something, probably best to stick with standard form and give the electric field in terms of its magnitude and the direction in the standard form. And then whoever's reading it will know, what angle to rotate through. If you have a picture, you can just give that angle and it's clear what direction you're talking about. All right. So any questions on these electric fields? One more thing I'll say, let's say we place a charge here. What would be the force on that charge? This one I actually like writing as a vector, because that's a very compact way to give us the magnitude and direction. Like, let's say we place a negative charge here. Let's say -2 microcoulombs. We place that there. So now the force on that, that's going to be, the magnitude is going to be Q times E. So remember, our electric field is newtons per coulomb. So you multiply by coulombs, you get the force in newtons. Now the direction, if we place a negative charge, when you multiply a vector by a negative number, it's like rotating it 180 degrees. So that would be the force on charge 3 if we placed it there. It would be opposite the direction of the electric field. So if we placed a positive charge here, the force would be in the direction of the electric field. For a negative charge, it would be exactly opposite that. Okay, so any questions on electric fields or electric forces? Okay, let's move on to chapter 19. I think we're skipping Gauss's law. Yeah, let's just talk about Gauss's law really quickly. So what Gauss's law says is that the flux through any closed surface is equal to charge enclosed over epsilon naught. So if we have, and again, we have to talk about flux, where, this formula, this is if we have a flat surface with an area A, and we have this normal direction. So if an electric field is passing through, crossing this surface, theta would be the angle between the electric field and that perpendicular direction. So flux here would just be EA times cosine theta. Now, if you had a curved surface, that complicates things. basically you'd have to break it up into little pieces. So we're not going to bother. I mean, we will. You can imagine, say, a charge, and if you surround that by a spherical surface, that's obviously curved. But in this case, if you just looked at a little piece, the electric field has to be in the radial direction, and the normal has to be in that direction as well. And so, in this case, the flux would just be the electric field times the total area, which is 4 pi r squared. So it's very easy to derive Coulomb's law from Gauss's law. You could do it the other way as well, which is why we say the two are basically equivalent to each other. And remember the charge density as well. Because in using Gauss's law, you have to be able to find the flux, but you might have to find the charge enclosed as well. And epsilon naught is just that number, 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. It's on the equation sheet. So, but sometimes maybe you have to find the charge. Like say you have a line of charge, just like you could have the charge density, let's say minus 2 microcoulombs per centimeter. So that means if you just have like a 1 centimeter section of this line, the charge would be minus 2 microcoulombs. And so if you make like a Gaussian cylinder around this, say with a length L, you could find the charge enclosed. So again, for Gauss's law, it has to be a completely closed surface. So you have a cylinder, these edges are part of the surface as well. And so the charge enclosed, it would just be from here to here. So that would just be lambda times L. So you might have to find the actual charge enclosed, and the flux in this case would be just E times the area of that cylinder, not including the two ends. Those two ends would have area as well, but there's the electric field lines would be perpendicular to the line itself because it's a negative charge. They would point towards the line. So the flux through these two surfaces is 0. So the area would be so like say this is a radius r. So again, just like a cylinder, you can imagine flatten it, just unrolling it so that it's flat. So this length here would be 2 pi r, the circumference of the circle, and then the other dimension is L, so it would give you the total area. And then you could you could find the electric field at a distance r from that line charge by using Gauss's law. So like these are parallel to the normal lines, so we don't have to worry about that cosine. So just applying Gauss's law, we'd have E times 2 pi RL. That would be the charge enclosed, which would be lambda L over epsilon naught. And notice that that L cancels out. So we can just solve for the electric field. And again, there's only a few cases where you can actually use Gauss's law to find electric fields directly. This is one of them. Point charges or spherically symmetric charges as well, or an infinite plane. All right. Let's talk about electric potential. Yeah, I think that's pretty much all the main topics from 18. So for 19, let's talk about electric potential. So we measure it in volts. So for a point particle, the electric potential at any point distance r away is K E Q over R. Electric potential is a scalar, but it has a plus or a minus sign. And that's the electric potential due to a single point charge. Now, if you have a lot of point charges, the electric field would you just add up the potential due to each charge individually and then add them up. So in that sense, it's kind of like electric fields, but we're dealing with scalars instead of vectors. So much easier to work with potential. And it's very nice that in the case of electrostatics, there's a relation between electric field and electric potential. Where if you want to know the electric field in a particular direction, you like say we know the potential everywhere. Let's say I want to know the x component of the electric field at this point P. So I'd pick a point delta x in the x direction. I'd look at the electric potential here, subtract the electric potential at the point we're actually interested in, and then divide by delta x. And that would give me the x component of the electric field. You can do the y component as well by picking a point in the y direction or the z direction. So you can get the entire electric field if you know what the potential is like in some region. Now, unfortunately, there is this approximately equal to symbol there. And that's because it depends on the delta x that you pick. However, if delta x is small, this becomes very close to being exact. And if you take the limit that delta x goes to 0, then the electric field becomes exact. We do not take limits in this class because it's not calculus-based. But yeah, there is an exact relation between electric fields and electric potential. And again, it complicates things if you have moving charges. So we're just dealing with electrostatics here. All right, so electric potential is very important because it, another way of looking at electric fields for one thing, if you know the potential everywhere, you know the electric field, and it's typically much easier to find the electric potential than it is to find the electric field. But let's actually do a problem. Let's do a two-dimensional problem with electric potential, kind of similar to the one we did before. Let's say, yeah, let's kind of do, I don't remember the actual numbers, but why don't we do the same thing we did before? I just don't remember the charges. I know Q1 was negative. I don't remember if those were the actual magnitudes of the charges or not. But let's find the potential at point P due to these two charges. So we find V1. That's 9 times 10 to the 9th Newton meter squared per Coulomb squared times Q1. Now, in this case, I'm actually going to plug in the minus sign. So I really emphasize when you're talking about electric fields, completely ignore that minus sign and just put the magnitude in. But in this case, we might as well put it in. And the reason why there's a difference between these two cases is because electric fields are vectors. You can't, an electric field has a direction, and unless you're strictly in dealing with a one-dimensional problem, you can't describe the direction of a vector with a plus or minus sign. But potential, it's a scalar. So the plus or minus sign is all you need there. So it's significant difference between electric fields and electric potential here. So yeah, we can put the minus sign and just put that out in front. The potential due to Q1 is going to be negative, and due to Q2, it will be positive. And then we divide by R, which is 3 centimeters. Now we do want to get volts out of this. So we're at unit conversion factors. We have a Newton times a meter is equal to a Coulomb times a volt. So let's throw that on there and let's see what we get. I'll just do that up here. We have Newton, meter squared, Coulomb, and volt. Everything should cancel out except for that volt. So we have Coulomb squared, meters, and then Newton meters. So we will get volts out of this. We'll get kilovolts or megavolts actually, because let's go with kilovolts. All right. So it's negative because Q1 is negative. We have 36 on top. 9 times 4 is 36. This would be 9, 10, 11 times 10 to the 14. Wait, maybe we do not. Yeah, I wrote that down wrong. So okay, that's better. So we just have 10 to the 11 on top, and then on bottom we have 3 times 10 to the 9th. So 36 over 3 is 12. And then we have 10 to the 11 over 10 to the 9, that's 100. So that's minus 1200 kilovolts for V1. Now V2 is going to be very similar, but we have to find R2. So we did this before. R2 squared, we have that distance squared plus that distance squared. So that'd be, in the x direction, we go 3 centimeters. Direction doesn't matter. So we square that, we get 9. Going up, we'll get another 9. So R2 squared is 18 centimeters squared. I'm going to take the square root of 18. So it's 4.24, let's say 4.2. So V2, we'll just copy this one just with the right numbers. So here we have 5 microcoulombs. And now the distance is the 4.2 centimeters. So we can put 100 on top. And then Coulomb volt over a Newton meter. And a kilovolt is 10 to the 3rd power volts. So if we do this, we have 9 times 5, we have 45 times 10 to the 11. On the bottom, we have 4.2 times 10 to the 9th. So 45 over 4.2, that'd be like 10 or 11. 10.7, so let's round that off to 11. And then times 100. And so now if we add these two, V1 and V2, minus 1200 plus 1100, we have minus 100 volts. At that point P. So we have a positive charge and a negative charge. So at that point, they nearly cancel each other out. If you look at V1 by itself, 1200 in magnitude. So the resulting potential at that point is much smaller. And yeah, so it just worked out that way. Q2 is bigger, but it's also farther away, which is why they kind of almost worked out that way, where they canceled out. All right. So that is electric potential. And capacitors, let's talk about that real quickly. So we'll use like a metal plate or pair of metal plates as our capacitor, even though it could be, I need two conductors. Yeah, this is the simplest example of a capacitor. You have two parallel plates with a cross-section area A and separated by a distance E. And yeah, if we, so again, it's a capacitor whether there's any charge on it or not. But if you charge a capacitor, means like putting a charge Q on one plate and minus Q on the other. So we treat it like a single object. We could say a capacitor with a charge Q. And if we do this, there will be a potential difference between the plates. We know we'll get an electric field from the positive plate to another plate. And this equation here actually becomes exact in this case. Because if you have a constant electric field, you don't have to worry about that approximately equal. It becomes equal. So like in between the two plates, the electric field would just be V over D, where V is a potential difference. But again, we treat a capacitor as a single object. So V would, like, we could set the, say, the negative plate to 0, then the positive plate would be at a potential V. So remember, electric fields go from high potential to low potential. And yeah, we can also find the electric field using Coulomb's law. So we've done that before. This is a review. So let's skip that. We can say for the capacitance, we could solve for it, but let's not. That'd be epsilon naught A over D. Okay. Now, any questions on capacitance? Okay, let's move on to chapter 20 and talk about electric current and circuits. So again, I made this bigger than I needed to and filled up the board. So let's define current. Charge over time. So like the net amount of charge that flows past the surface, if you divide that by the time it takes for the charge to flow past the surface, that would be the current. In a very unrealistic picture, say we have a current flowing down a wire, very unrealistic, but you can just picture a bunch of positive charges flowing in the direction of the current. Now, a better picture would be picture negative charges flowing in the opposite direction. But an even better picture would be picture negative charges moving in both directions. They just have a tendency to move to the left more than the right. So yeah, that would be a more realistic picture. So this idea of just charges flowing down the wire in a nice orderly fashion, not at all realistic. All right. Let's get to circuits now. And again, we deal with circuits with just a battery, which has, let's see, electrostatic potential, or the EMF, electromotive force, sorry, that would be measured in volts. Let's actually do a circuit. We don't have to start from the beginning to review. So let me try and come up with a circuit that we haven't done before. Kind of limited how many variations we can get. Let's do this. So let's say the battery is 9 volts. I'm just making up numbers here. So we've got these 4 resistors, and let's just do this problem and say we're done with section 2. So what I mean by do this problem, we want to find the, let's make a table. We have a battery. R1, R2, R3, and R4. And we want to know the current. Yeah, let's say the voltage, current, and power. I don't know if I left enough room to actually write this stuff down, but so for the battery, we're given the voltage. And we're going to find like the current flowing through each element, the voltage gain or drop across each element, and the power either delivered to the circuit or dissipated from it. So that is our goal here. So let's, we've got our loop rule and our junction rule. So let's call this I1, this I2, and this one I3. So, yeah, and what's, every circuit is a little bit different, but the one thing, and there are exceptions, but not anything we'll be doing in this class, but the first step, regardless of what circuit you're talking about, let's find the equivalent resistance first. So the equivalent resistance of the entire circuit. So to start out with, we can add R2 and R4 in series. So that would be 11 ohms here. So like this branch has 11 ohms, R3 is 4 ohms. Yeah, let's call that, let's just call it RP for parallel. We have 1 over R3, so that'd be 1 over 4 ohms. And then we have 1 over 11 ohms. So let's get a common denominator of 44 ohms. So here we would have, on top, we'd have 15. So here we multiply by 11 over 11. Here we multiply by 4 over 4. So the common denominator is 44 ohms. So 11 plus 4 is 15. So 44 over 15. Let's do that. So I'm getting 2.93. So like this here is 2.93 ohms. So like this whole combination. And so we could rewrite the circuit. I'm going to erase some of this so we have room. But now we have R1. And we combine this whole thing here. So like R1 is 6 ohms. And then this combination is like a single 2.93 ohms. So the equivalent resistance of the circuit is 8.93 ohms. Okay, so that is the first step, regardless of what your circuit looks like. And again, there are possible exceptions where you can't do this, but that you don't have to worry about that. So I'm going to erase this now. So basically what that means is if we just put like a box here, we can't see inside, we can tell whatever is inside there. If we put wires, try to establish a current through it, the resistance it'll see is 8.93 ohms. So without knowing the details of what's inside, that'd be the equivalent resistance. And so we can use that to find the, I should write Ohm's law. I'm out of room, but Ohm's law definitely deserves to be on the board. And we'll just erase or move that up. So the current then, I1, the current leaving the battery, that'd be 9 volts over 8.93 ohms. So it's about 1.008. So basically, let's just say 1 amp. Now, when we get to the resistors, again, this is where the details of the circuit matter. But remember, we know all of the resistors in this circuit. And so if you know one of these two columns, you'll automatically know the other. So if you can find one element, you can immediately find the other using Ohm's law. And again, we ignore this power column until the end because power is just current times voltage. So once we have these two filled out, third one will be trivial. But it's an important one, particularly for checking the final result. But now let's look at here. I1 is going to flow through R1. So we know that's going to be 1 amp. And since V is IR, the voltage drop here is going to be 6 volts. Worked out rather nicely that the current just leaving the battery happened to be 1 amp. Okay, but now the current is going to split up. And remember the loop rule. Let's look at this inner loop. The sum around the loop has to be 0. So here we have plus 9 volts going across the battery, minus 6 volts for the first resistor. So the voltage drop across R3 has to be 3 volts. And it's a voltage drop. I'm just writing the magnitude now. You can put the minus sign in if you like, but yeah, I'm not doing that right now. And so we can find the current here. Current, let's call that I3. Yeah, that is what we're calling it. That would be the voltage drop across the resistor, which is 3 volts, divided by R3, which is 4 ohms. So that'd be 0.75 amps. And so now we want to look at our junction rule. We have a junction here. So what's going into the junction is 1 amp. And if 0.75 amps goes this way, then 0.25 amps has to go the other way. And so now, in a sense, we're done because we can find the voltage drop across each of those just by doing I times R. So for R2, that would be 2 volts. Now it's 1/4 times 8 is 2. And for R4, 1/4 of, wait, these numbers. I want to check these numbers again, but yeah, there should be some round off errors, but let's see. For R4, we have 0.25 amps, 3 ohms. That would be 0.75 volts. So yeah, something is not adding up. So let's make sure. Check I3 again. I wonder if rounding off to 1 amp actually made a difference here, because these numbers aren't quite checking out. R2 plus R4, like those voltage drops, that should be 3 volts. I don't know if we should be off by 0.25 or not. That seems a bit high. So let me go back to the beginning and just check the numbers real quickly. So if we do 1/4 ohms plus 1/11 ohms, yeah, that would be 2.93 plus R1 is 6. So yeah, 8.93, that checks out. So I1, that would be 9 volts. I'm going to do 1.008 and just see if the numbers work out any better. Now, well, if we were actually doing labs, like actual physical labs in this class, you would know that this is not likely that we'd be able to measure currents that accurately using the equipment we have in class. So typically we would not want this many significant figures, but we only round off at the end. So I want to make sure that these numbers are working out. Because this one, that's a little bit farther off than I'd like. Actually, we already indicated volts and amps, so let me put those numbers in. Okay, so now the voltage drop across R1, we have 1.008 times 6. So 6.048. Which means R3 would be 2.952. So you have to add up those to get 9 volts. So again, we're saying there's no significant drop for the wires themselves. Yeah, so that works out. All right, so now let's find the, the current here. Now for R3, I3 would be 2.952 volts divided by 4 ohms. So a volt over an ohm is an amp. So 0.738. So that's the current. So again, what's going into the junction is 1.008. So if we subtract 0.738, we get 0.27 going the other way. So I'm doing all the exact same calculations, just with more significant figures. Yeah, So I didn't like the well, it might have just been a round off error. That was a little bigger than I like. So now the say V2 would be 0.27 amps times R2, which is 8 ohms. So 0.27 times 8 would be 2.16. And then our V4 would be 0.27 amps times 3 ohms. So 0.81. So now let's check our loop rule. For this loop here, we're guaranteed to get that to work out because we used it to get the voltage drop across resistor 3. So basically, these two should add up to 9. Voltage drop across R1 and R3, that has to equal the battery. But if we look at this outer loop, we should have V1 plus V2 plus V4. I'll put a question mark there. So yes, outer loop, we have the battery giving us 9 volts, so we have to drop 9 around the rest of the circuit. That'd be R1, R2, and R4. So if we add these up, we should get 9 volts. So that wasn't working out too well last time because of rounding, but let's add this up. So 6.048. V2 is 2.16, and then 0.810. So I'm getting 9.018. That's a much better result than I had last time. So yeah, everything we did before was right. Just I rounded off a bit too much early on. So it led to some significant questions about whether or not the loop rule and junction rule were holding up. But yeah, this checks out now. So the final check, let's look at power. So here, 9 times 8 is 72. So of 1.072. The rest of these are going to be negative. The resistors are dissipating energy. So let's look at, again, power is current times voltage. So 1.008 times 6.048, that's 6.1. Or that should be 9.072, not 1.072. So we check that. I'm going to make room. So again, we'll check for the power column. This should add up to 0. So we'll add up the power dissipated by the resistors once we figure out what those are. So now we have 2.16 times 0.27. That's 0.58. I'm rounding off a little bit more than before just because it's amount of room. So multiplying these, 2.2. Finally, 0.81 times 0.27, 0.22, or just 0.2. So let's add this up. Let's say 9.08 is what we should get. So 6.1, 0.58, let's round that off to 0.6, 2.2, and 0.2. Oh, this will work out better than expected. It's like all the rounding errors canceled each other out. Oh, yeah, we were supposed to get 9.072. Fairly close. And again, if we carried more significant figures in the calculations, that would have worked out. So that's a good check. If you add this total column at the end, you should get 0 and are close to it with rounding errors. Okay, so that was about an hour for the first section. So are there any questions on this one? Okay, so I'm going to stop recording. I'll break it up into pieces.